In this lecture, we're going into the details of how a radio telescope actually works. Radio telescope systems, the nuts and bolts. Let's begin by looking at a number of radio telescopes around the world. They're all being used for research. They're all unique, and most of them are the absolute best at what they do. I'll give a few science highlights as well, and we'll cover those in later lectures. This giant reflector is near 𝐷𝐸𝐴 in Puerto Rico. It's 1,000 feet across and it fills a valley. It's the telescope that was used to discover a pulsar so important that its discoverers got the Nobel Prize in Physics. Next we go to Green Bank Telescope, whose dish measured rim to rim is 110 meters by 100 meters. That's 360 feet by 330 feet. We'll take an in-depth tour of this telescope in a couple of lectures from now. Here's a telescope in Germany peering up out of a narrow valley. This telescope is 100 meters across. For many years, it was the largest fully steerable radio telescope. It's made many important maps of radio emission from the Milky Way. Next, we go to the radio telescope at Jodrell Bank in England. This one was built in the 1950s. It's 250 feet across, about 76 meters. You can see that I'm going from larger to smaller. This telescope has been involved in everything from tracking Sputnik, the first satellite in orbit, to measuring the properties of pulsars. Now to a telescope in India, part of the giant meter wave radio telescope outside Pune. This dish is 45 meters in diameter and its surface is made of mesh. It's a powerful telescope for measuring hydrogen in galaxies. Next we go to a mountaintop in Spain, where a collaborative group of French, German, and Spanish scientists operates a radio telescope 30 meters in diameter. This telescope has been used to study gas clouds in the Milky Way that are on the verge of creating new stars. Finally, to the Atacama Desert in northern Chile, where an international collaboration involving Europe, North America, Asia, and South America has built an array of dishes, each 12 meters in diameter. This telescope is not even completed yet, but is already producing breathtaking images of solar systems while they are being formed. In our Rogues Gallery of radio telescopes, we've jumped in scale from 𝐷𝐸𝐴, 1,000 feet in diameter. That's a telescope so big it had to be photographed from the air, to 12 meters, about the size of a house. Let's notice two things right off. First, no two of these radio telescopes looks anything alike. Of course, they're all dishes, sort of, but there the resemblance ends. Second, where are the domes? That's how an observatory should look, right? Telescopes in domes. What's wrong with these radio people? Here's a quick answer to the dome question. The smallest radio telescope in my Rogues Gallery of radio telescopes is about the same size as the absolutely largest optical telescope on Earth. Let me say that again so that you grasp the scale of these instruments. There are two telescopes of the Keck Optical Observatory on Mauna Kea in Hawaii. They're among the largest optical telescopes in the world. Their mirrors are 10 meters across, 10 meters. Here's the smallest radio telescope I showed, one of the ALMA dishes in Chile. Its dish is 12 meters across, about 6 feet larger than the Keck mirror. Now sure, there are some radio telescopes that are sheltered in domes, but the vast majority are not. A dome the size of a 30-meter radio telescope would be an enormous structure, and a dome that enclosed one of the 100-meter class dishes would cost nearly as much as the telescope itself. And another factor you must know is that we do pretty well without domes because the tolerances on a radio telescope are a lot looser than the tolerances on an optical telescope. We'll talk more about that as we go on. Let's do a quick run through our radio telescope gallery again before getting into the details. 𝐷𝐸𝐴, Puerto Rico. Green Bank, West Virginia. Effelsberg, Germany. Jodrell Bank, Great Britain. Pune, India. Pico Veleta, Spain, Atacama, Chile. What do they have in common? Well, they're all based on a dish of some sort, a dish to reflect and concentrate the incoming radio waves to a point where they can be picked up and amplified. Now, besides their size, how do our different radio telescopes differ? First, there's the material of the dish. India's GMRT on the left is mesh, while the others I showed use mostly solid metal. Here's a GMRT dish and the 140-foot telescope at Green Bank. They're about the same diameter, but one has a mesh surface, the other is solid. Second, there's the way that the dish is supported, the way it's held up off the ground, and the way the telescope is designed to point at different directions on the sky. Each of the telescopes was optimized for a specific function, and that accounts for 90% of their difference. But they have a lot, quite a lot in common, and we'll begin with that. Here's a schematic of your basic modern radio telescope. A radio telescope is a thing that collects radio waves from a certain direction in the sky, focuses them onto a point where a receiver can pick up the signal. The receiver does a number of other things, including amplify the signal. The signal is then passed along to systems that detect and measure it. That's it. Pretty straightforward, isn't it? Let's zoom in on the smallest piece of the entire apparatus and see what it actually means to capture a radio wave. The radio waves are funneled in from the left and hit that wire in their path. This wire is not fundamentally different from wires that we see every day. Its most important property is that it will carry electricity. We call this particular wire the probe because it probes the electric field. The wire, the probe, is made of a metal like copper or aluminum. These common metals have a lot of free electrons swimming around on their surface. Electric current is just an organized motion of these electrons. You push the electrons from one end of the wire, and the signal travels along as electricity. You can push electrons by hitting them with an electromagnetic wave. And when that happens, the wire has become an antenna. An antenna is a device that intercepts an electromagnetic wave in free space and turns it into an electric current in a wire. The antenna for the radio in your car does the same thing. It catches incoming radio waves and turns them into a current in a wire. It's easy to visualize. At the heart of every radio telescope is an antenna, some bit of wire or a metal rod that captures the incoming electromagnetic waves and puts out an electric current. The current looks like a wave running down the wire, and the amplitude of the wave, the height of the wave, is called the voltage. The purpose of a radio telescope dish is to capture as much radio energy as possible and focus it on that little bit of wire. By the way, the radio telescope that Ewan and Purcell used to detect the 21-centimeter line of hydrogen was just a horn with a probe. For maximum efficiency, the probe should be 1/4 of the size of the wave it's going to intercept. For the 21-centimeter line, that makes it about 5 centimeters in length. But for waves of a few millimeters, it can be quite small. Back to the dish. The radio signal hits the dish and reflects up to what we call the primary focal point, or the prime focus. Here we can either catch it with an antenna or redirect it using another reflecting surface to send the signal somewhere else. This dish has a secondary reflector that redirects the signal down to the big horn in the middle of the dish where the receiver sits. Here's a dish with the receiver at the prime focus. Let's stick with that for now. So, we've concentrated the radio power on a little antenna, which turns it into an electric current in a wire. Now what? The first thing we do is amplify it. We feed the signal into a device that makes it stronger by many times, 1,000 times, so that it turns from a faint celestial whisper into something that we can measure. We're here in one of the electronics labs at the Green Bank Observatory, and this is the place where engineers design the electronics that makes radio astronomy possible. They design these fantastic, unique receivers, and then the parts are built in our machine shop here at the observatory. We've got here the prototype of one of our receivers, This was built to test certain principles, and once they got this right, a different version was built and is now installed at the Green Bank telescope. Let me explain how this receiver works. This is the feed horn for this receiver. This is to work at about a wavelength of 1 centimeter, and you can see this is about 10 centimeters across. The ribs control the reception of the electromagnetic radiation very precisely. And this sits up here on top of the receiver. Now it'll be covered by a protective cover, and this whole part of the receiver will be enclosed in this aluminum tube, making it a vacuum doer. And this refrigerator down here will pump the temperature down to just a few degrees above absolute zero, somewhere around minus 450 degrees Fahrenheit. So the signal comes in the feed horn and then goes right away to this device here, which splits the two polarizations into a wave going this way and a wave going that way. They'll be kept separate from now on because they each contain independent information. The two polarizations then come down to this device, which adds a known amount of noise in regular pulses. That way we can calibrate the amplification of the system. Once the noise is added, it goes into the amplifiers here, which actually amplify by factors of several thousand the signal, which then goes down further and out of the cold doer onto fibers where it's sent back up to the lab for analysis. All of these parts here are kept cold, and so the refrigerator sucks heat out of this tower here, and the devices are attached to the tower by these straps. Many of these devices scale in size depending on the wavelength or the frequency at which they're operating. This operates around 1 centimeter wavelength or 25 to 30 gigahertz. Here we have another example of a feed horn for a much lower frequency, much longer wavelength. Again, this was built in our shop here and designed by our engineers. There are other examples too we have here of some of this equipment. For example, this beautiful device here is another way of splitting the incoming wave into two polarizations. In this case, this tap here has a probe that goes in behind the waveguide, and out comes polarization going this way, and this tap has a probe going in, and out comes polarization going in this direction. This is an example of a complete receiver that's going to go up on the Green Bank telescope. This part will sit on the top of the receiver room in the turret and be exposed to the elements. The feed horns are in here, covered by this membrane. And this part will hang down in the receiver room. The signal comes in here and then into the electronics in the doer here. And within the doer, that's where the temperatures get very cold. And then the signal after amplification will come out of the doer, be processed by this electronics, and sent over fiber back to the lab for analysis. Now you may ask, if you can amplify a signal by 1,000 times, why go to the bother of building this big dish with a big aperture when you could have a smaller aperture, a much cheaper dish, and compensate for the weaker signal by adding more amplification? An excellent question. The answer goes back to our discussion of thermal radiation, the radio radiation emitted by every object that acts anything like a blackbody. Amplifiers act somewhat like blackbodies, and this means that not only are they amplifying the incoming signal, at the same time they're putting out their own signals, radio noise, that's indistinguishable from the radio signals coming from the antenna, and the noise gets amplified along with the signal. If our antenna wire does not carry electricity perfectly, if it has even the slightest resistance, it acts a little like a blackbody. For example, if only 1% of the astronomical signal is lost to resistance in the wire, then that same wire adds 1% blackbody noise at the temperature of the wire. The astronomical signal is lost and it's replaced by noise. For this reason, most of our receivers are cooled to a few degrees above absolute zero. The colder the blackbody, the less it radiates, remember? Receiver noise can swamp the celestial signals. We make great efforts to keep our receivers quiet, but nothing beats starting with the strongest astronomical signals possible, which means the biggest aperture. In our schematic of a radio telescope system, the receiver is always located at the focal point because even the best wires have loss and introduce noise. We want the amplification to occur as close to the antenna as possible. So, our radio signal has been captured by a little antenna, converted into a current and amplified. And in the process, noise is added, regrettably but unavoidably. What next? Well, what's next is one of the marvels of radio engineering, and it allows radio astronomers to use techniques that are simply impossible in other parts of the electromagnetic spectrum. What's next is that we change the frequency of the signal while preserving all the information it contains. This technique is called heterodyning or mixing. Here's one way of looking at it. Let's say that we want to measure the radio spectrum around the 21 centimeter line at 1420 megahertz. We point our dish at a piece of the sky, and here's what we get. This is a chunk of the radio spectrum, about 3.5 megahertz wide, centered at 1420.5 megahertz. The height of each point shows the power we've detected at each frequency, and that bump in the middle is the 21 centimeter hydrogen line. Now, let's shift it down by 1300 megahertz. Voila! The exact same data, only now the 21 centimeter line is centered at 120 megahertz. So you might ask, why bother? What's the big deal? Here's the big deal. Suppose that you wanted to measure the 21 centimeter line over very fine frequency intervals. For example, suppose that you wanted to get a very precise Doppler shift velocity of the peak. Let's imagine that we do it by building a narrow set of filters, each 1 kilohertz wide, and put the spectrum through them. Each filter measures only the power in a narrow band and rejects the rest. We measure the output of each filter, and there we have it, a precise measure of the 21 centimeter line. Here's what we might build. We'd have a filter that worked from 1420.000 megahertz to 1420.001 megahertz. Next to it, another filter that worked from 1420.001 to 1420.002, and so on. That would do the job. By the way, we would call a bunch of filters a spectrometer and call each of the filters a channel, like a TV channel. A spectrometer is a device that measures the amount of signal at a number of different frequencies. But now, suppose that for another project, we wanted to measure emission from the OH molecule at 1667 megahertz and measure it every kilohertz, just like we did for the 21 centimeter line. Because the OH molecule radiates at 1667 megahertz, we'd need a completely new set of filters. One filter, that is, one channel, would run from 1667.000 megahertz to 1667.001 megahertz, and so on. We need a new spectrometer. And if we wanted to measure the ammonia line, which comes in at 24,000 megahertz, we'd need filters from 24,000.001 megahertz to 24,000.002 megahertz, and so on. Yet another spectrometer. We'd have to build a completely new system every time we wanted to study a different set of frequencies. But if we mix all of these signals down to, say, a band of frequencies around 120 megahertz, we would have to build only one set of filters that run from 120.000 to 120.001 megahertz, and so on. We would only need one spectrometer. It would not matter what sky frequency the receiver was amplifying, because when it hit our spectrometer, it would be mixed down to 120 megahertz. By doing this, of course, we would have to keep track of what the original sky frequency was, write it down on a piece of paper somewhere, because our spectrometer would not know. If you own a radio, you will see that it covers a number of bands, AM, FM, maybe others. That means that radio signals are coming through the air at frequencies like, say, 106.3 megahertz, that's in the FM band, or 1370 kilohertz in the AM band. But our radio uses heterodyning to mix those signals down into the audio range, kilohertz, where our ears work. The speakers in our radios don't know the frequency of the radio station, because by the time the radio signal gets down to the speakers, it's been mixed down to audio. Before we go on, let's talk a little more about terminology. Because radio astronomy developed out of radio communications and radar techniques, we've inherited a lot of jargon from bygone days. Some of the jargon is useful, but some is not. So in this course, you are not going to hear me refer to microwaves, except when I'm talking about an oven. Microwave was an early designation for radio signals with wavelengths shorter than shortwave. In my opinion, that term is no longer useful at all. As far as I'm concerned, it's radio all the way up to the infrared. Back to our stroll through a radio telescope system. We've collected the signal that passed through the aperture using the dish, focused it onto an antenna, which turned the electromagnetic radiation into current flowing down a wire, amplified the signal, mixed it to a convenient frequency, and actually, I've gotten a bit ahead of myself because I already discussed detecting the signal. The process of detecting the signal means converting the current running down a wire into a measurement of power. This is done with a device whose generic name is a detector. We use various technologies to detect the power received by the telescope. A detector always averages over some band of frequencies. If we are just studying the general properties of an object emitting blackbody radiation, the band can be quite broad, because the intensity of blackbody radiation does not change rapidly with frequency. If we are looking at details in a spectral line, the individual bands we measure, the channels in our spectrometer, can be quite narrow, but the result is always the same. We end up measuring power, and that is the voltage squared, at a particular frequency coming from a particular direction in the sky. These days, our detectors are digital, and their output goes straight into a computer where it is stored and analyzed. Let's return to the 21 centimeter hydrogen spectrum and make sure that we understand exactly what it's showing. There are more than 4,000 channels containing information in this spectrum. Each one shows the power at a particular narrow frequency band less than 1 kilohertz wide. This spectrum is an average over 4 seconds of time. It's a kind of snapshot of the sky in one direction at one time over a range of frequencies. Do you notice the fuzz on the spectrum? The random points jumping up and down? That's noise. The early radio astronomers used chart recorders with pen and paper to show the change in incoming power with time or position or frequency. This chart recording was made while I was using the 300-foot radio telescope at Green Bank during graduate school. Several computers were running at the same time recording the data, but a chart gives a good overall indication of what's coming through the receiver at any instant, so I had it running as well. Here we have only 4 channels, and they are averaging over many megahertz. I was tracking a specific spot in the sky. The chart shows the radio signal at those frequencies as time goes on. Time increases from left to right. For this project, the telescope was used to observe pulsars, and those spikes you see are individual pulses. Those spikes are bursts of radio emission from a spinning neutron star. The pulses come in clusters, and the clusters are caused by scintillation, a kind of interstellar twinkling effect that causes pulsars to brighten and fade on time scales of minutes. Let's go back over the radio telescope system. The incoming wave that comes from the direction that we're studying is reflected and brought to a focus, where a receiver amplifies the signal, and it's sent to a detector for measurement. Now let's look in detail at how a dish works, how the shape of a dish focuses radio waves. The simplest radio dish has a shape of a parabola. A parabola is symmetric about this central line called the vertex line. You spin this 2-dimensional curve about the vertex line to create a 3-dimensional dish that we call a paraboloid. A radio wave that comes through the aperture perpendicular to the vertex line, like the dotted line in the figure, will be reflected off the dish, and all parts of it will arrive at the focus at the same time. The wave will be in focus. The reason this works is that it's a property of a parabola that the distance from any point on our incoming wave to the focus is the same, no matter what part of the dish it hits. In the drawing, the 3 parts of the wave that hit the dish at 3 different places all arrive at the focus at the same time because they all traveled the same distance. They arrive in phase with each other. The signal is concentrated, it adds, it's picked up by the antenna and amplified by the receiver. What happens if the wave is not perpendicular to the vertex line, but is off at some angle? We see that the right part of the wave will arrive at the focus first because it has a shorter distance to go. The left part of the wave has a longer path, so it arrives at the focus later. The 2 waves do not arrive in phase at the focal point. I've used the word phase, and that refers to a wave cycle. It's often measured in degrees, with 360 degrees being a full cycle. That comes from the 360 degrees on a circle, and you can imagine a wave mapped onto a circle. We can locate the position on the wave by a measure of its phase in degrees. Here's what happens when we add electromagnetic waves together. Here we've got a wave coming straight into a dish. I've colored 1 part blue and another part red. Because the 2 parts travel the identical distance, they arrive in phase, and the 2 lie exactly on top of each other. When they combine, they make the wave in purple. Now let's increase the path of the red part of the wave relative to the blue part. The red part now has been delayed because it had further to travel. The 2 waves are somewhat out of phase and don't add to get full power. Notice that the height of the combined wave has been reduced a bit. Delaying the red part of the wave reduces the sum even more. The parts of the wave are canceling. And even further delay gives us this. And finally, they're nearly totally out of phase. The 2 parts of the wave have nearly canceled, and we get very little signal from their sum. If you've heard the expression that someone is 180 degrees out of phase, it means that they are completely wrong. For waves, it means complete cancellation. Let's plot the height of the sum of the waves as the phase shifts. This shows why radio dishes have a maximum sensitivity in one direction and less sensitivity in other directions. This is true of all telescopes. We don't want signals from some random direction getting into our receiver. We want only the signal from the direction we're pointed. Now this next bit is important. 2 consecutive peaks of any specific wave are exactly 360 degrees apart in phase. But that doesn't tell us anything about the actual distance between the peaks, which is their wavelength. When we say that Carl Jansky measured the sky at 20 meters wavelength, we mean that the distance between the peaks of his radio waves, between the wave oscillating over 360 degrees of angle, is 20 meters. What does it take to change the phase of a wave by 180 degrees? A wave of 20 meters wavelength would have to be delayed by an extra path length of 10 meters. That would put it out of phase with the 20-meter wave that was not delayed. But a wave of only 2 centimeters wavelength, a little less than an inch, would only have to be delayed by 1 centimeter to be totally out of phase. So phase error is something that's not absolute, but depends on the wavelength of the signal you're studying. Let me go into this just a little more so that we all get the point. Let's imagine that our radio dish is a perfect parabola everywhere, but in one section, where a bit of falling ice from last winter's big storm made a ding in the surface. Now at this point, we're wishing that we were in a dome, but we're not. And we've got a divot, a dimple, a depression in the surface of our dish of, let's say, 1/2 centimeter. Let's see what effect this has on a wave with a wavelength of 20 meters, Jansky's wavelength. The 1/2 centimeter depression means that the waves hitting that part of the dish have to travel an extra centimeter on their journey to the focus. An extra 1/2 centimeter before they hit the dish, then that extra 1/2 centimeter to get back up to where the dish should have been. They're delayed by a full centimeter. Here's our phase diagram of a 20-meter wavelength wave arriving on time, overlaid by one delayed by a full centimeter. You can't see the difference because there is no difference to speak of. A 1 centimeter delay in a 20-meter long wave is less than 1 part in 1,000. It makes no difference at all. But now let's see what happens with the same surface if we are using it to detect radio waves at 2 centimeters wavelength, a frequency around 15 gigahertz. All of a sudden, our 2 centimeter wavelength waves find themselves delayed by an entire half wavelength, and the waves that hit the bad spot on the surface will cancel some of those that hit the good surface. The lesson is clear. The accuracy we require of our dish surface depends on the wavelength where we want to use it. And shorter wavelengths, meaning higher frequencies, require a more precise dish than is needed at long wavelengths. Here's the rule of thumb. The surface accuracy, and by this I mean the deviation of the surface from a perfect parabola, should have a root mean square error of less than about 1/16 of the wavelength you want to observe. To work at wavelengths of only a few millimeters, our surface had better behave like a perfect parabola with deviations no larger than a fraction of a millimeter, the thickness of a standard business card. On the other hand, to work at a wavelength of 21 centimeters, in the hydrogen line, we could tolerate surface errors, of a centimeter or so. If the reflecting surface of our 100-meter diameter radio telescope had to have a mirror finish, it would be almost impossible to build, and we'd put it in a dome. In fact, the new generation of big optical telescopes, now under construction, have diameters of 30 or 40 meters and are in domes. But because of the relatively large wavelengths, we can bring our radio waves into focus using less perfect dishes exposed to the elements. We've covered quite a bit of ground today, but there's one final topic: polarization. So far, I've treated electromagnetic waves as if they simply went up and down. The up and down wave excites up and down motion of electrons in our antenna wire that becomes the current we detect. But electromagnetic waves can have a side-to-side component as well. And if we imagine a wave coming in and out of the screen, we can see that it won't be picked up by our antenna wire because the wire is oriented up and down. This property of electromagnetic waves is called their polarization. The radio waves from most astronomical sources are not polarized, or polarized only slightly. This means that their orientation is mostly random, changing rapidly from horizontal to vertical and everything in between. Now, transmitters on Earth are polarized, and with a small portable radio, you can quickly demonstrate that the antenna receives the strongest signal at one particular angle. A single antenna wire is sensitive to just one segment of the polarized wave and only picks up 1/2 of a randomly polarized signal. So we have a parallel system to pick up the other half. That way, the full signal is detected. Each polarized antenna connects to its own independent set of amplifiers and detectors. We've covered quite a lot today, but it will help us appreciate what we'll see when we visit the Green Bank Observatory. Thank you.